Welcome to Chapter 11, Section 3. We are now going to be talking about period frequency and wave speed here in Section C. So what we're going to do in this section of the video is we are going to apply the relationship among wave speed, frequency, and wavelength in order to solve problems. So wave motion, right? Like with simple harmonic motion, we can use frequency and period to describe our waves. So from these meaning the frequency and period, okay, and the wave's wavelength, we can actually calculate the velocity of a wave as it travels through a medium. So the speed of a mechanical wave is constant for any given medium regardless of the frequency or period. What that means is that t can change, f can change, but as long as it is, say, a sound wave in air, okay, as long as it's a sound wave in air, right, where air is our medium, okay, then as long as that sound wave is in air, its velocity is constant. It will not change. Okay, now if the sound wave travels to water, its medium has changed, and so its speed will change. Okay, and this is true for any medium and any type of wave. Okay, so the speed of a mechanical wave will only change when the medium is changed, like going from air to water for sound. Okay, then the velocity will change. So here we have some additional variables. Okay, so we use v for velocity like before, f for frequency, t for period, and lambda is the Greek letter. Okay, so the Greek letter lambda, that is what we use for wavelength. And I don't know if it's the proper way to write it or not, but the way that I write it is I do the up first and then I drop that down. So the equation that we have then for finding the velocity of a wave is just that the velocity is equal to the frequency times lambda, okay, the wavelength. If we had period instead, we could also write this v equals the wavelength divided by the period, and that would be the same equation. So let's do a little practice with this now. So a piano emits a frequency in ranges from a low of 28 hertz to a high of 4200 hertz. So we're going to find the range of wavelengths in air for the piano when the speed of sound, and this is in air, is 340 meters per second. So the things that we know, right? We know our equation, v equals f lambda. Okay. And we know that our frequency is going to be a range. So really we have two things for frequency. We have 28 hertz and we have 4200 hertz. So we've got two of those. And I'm just going to make things easier, I'm going to call this one A and this one B so that we can find the frequency of A and B. And then the velocity of sound in air is 340 meters per second. So now if I'm going to start plugging some things in, we're going to do A first. Okay, so we know that we have our equation up here. So plugging things in, we end up with 340 meters per second will be equal to 28 hertz times our wavelength. And solving for the wavelength then, and this is the wavelength of A, the wavelength of A will be equal to 12.1 meters. We do the same thing now for B. So we plug things in. This time we're using our 4200 hertz, so we still have the same speed. 340 meters per second will be equal to 4200 hertz now, times our wavelength B, and solving for our wavelength of B, we get a value of 0.08 meters. So that wraps up Section 3, Part C. Go ahead and let me know if you have any questions in class, and I will see you there.